Welcome to another RDWorks Learning Lab. We're back in the workshop today and we're going to continue with our lens saga. We're going to dig deeper into Pandora's box because it seems absolutely bottomless. We've still got to fully understand how lenses cut. Now, in the last lens session, I did something that was both puzzling to me until I decoded it, and it was certainly very puzzling to other people. So what I plan to do today is to repeat, but in much more detail and single steps, the procedure that we tested last time for proving that there was something happening way beyond the natural focal point of a lens. Because people jump in and out of these videos and on their own they mean nothing. So what we're going to do, we're going to start off today by talking about how materials and light interact. We all know what they are. They're waves. Now, that's supposed to be an ear. And when those waves hit your ear, they're sound waves. And those sound waves are little pulses of pressure which will make your eardrum vibrate so that you can actually hear sound. Now here we've got an atom, another atom and another atom, and we've got some different sorts of atoms in here, and this makes up a material which is stuck together with all different strengths of effectively magnetic forces. And I'm not really meaning magnetic forces, but there are forces of attraction which hold that structure together. And that is a molecule. It is just what it looks like. It's a bit of a wobbly structure. You know, all these things are hanging it together, and this molecule is already doing this naturally. It's vibrating. Okay, now when you start to fire, light waves at the molecule, it's a complete analogy to what we've just seen here, firing sound waves at your ear. So the only difference between those two is the frequency of the waves. Your ear responds to something in the 1000 Hertz region, maybe up to 15,000 Hertz, and molecules respond to something in the region of a terahertz, which is like 1,000 billion cycles a second. And the way that this machine works is it supplies light at a single frequency and it vibrates molecules. And the more you vibrate a molecule, the hotter it gets. The point I've made to you many times before is that there is no heat in a light wave, there's energy. And that energy converts into heat by making the molecule vibrate. And the vibration level in a molecule is its temperature. So if you can make it vibrate faster, it will get hotter. Remember, it's not the material that's getting hot, it is the molecules. The fact that there's a lot of molecules in the material means your material gets hot. But you're not heating the material, you're actually stimulating a molecule to make it heat up. And the point is, when you heat this material up and it vibrates sufficiently fast, these bonds, some of them, which are all different strengths, will break down. And maybe this brown one here will fly off. And maybe this brown one will fly off. But they're bonded in different ways, so they will break away at different temperatures. Okay, and as they break away, this brown molecule may decide it's happy to bond up with something else. Maybe it'll find a couple of yellow atoms out here which it will join with. So it will now make a new material. And that's what happens when we work with this machine. You think we're burning the material, but really what we're doing, we're shaking the molecules to pieces. And we're making the atoms loose, and they're flying around and they're joining up with other atoms to make new molecules. So when you burn paper, you get ash. Ash is not paper, it's a new material. And the only reason we get from paper to ash That's because we vibrated the molecules and we made the molecules fly apart. It's relatively that simple, the way in which this machine works. In the same way that sound you can hear with your ear, but if you make the sound frequencies low enough, you might just be able to hear it with your ear, but when the volume starts getting turned up, you feel it vibrating in the cavities of your body. You must have experienced that if you've been to a pop concert or something, you know. You feel the music. And equally well, if you start increasing the frequency to things that bats can hear, we can't hear it. There's still noise there, but the frequency is so high that it won't actually vibrate the ear enough so that you can hear it. Well, that's basically the same happens with light waves. If you change the frequency of the light wave, it will affect the materials that you're firing it at in a completely different way. Some materials will vibrate easier and some materials will vibrate less easily. If they vibrate easily, you can heat them up quickly. If they vibrate in a slightly more lethargic manner, it takes more time and effort to heat them up. A good example of that with our 10.6 micron wavelength is acrylic and wood. Acrylic, even though it heats up and starts self-destructing at 200 degrees C, it actually cuts half the speed of wood, which has to heat up to about 3000 degrees C to disintegrate the carbon. There is a complete range of properties associated with molecules and frequencies of light. Different frequencies of light affect different materials in different ways. Now, before we can use the laser beam from this machine, we have to put it through one of these things, which is a lens. And I've got some lovely new lenses here from China. Now, when you amplify sound waves, you make the volume louder. It's not quite the same analogy when you start amplifying light waves. So if we can squeeze more light into the same space, the light becomes more intense. And that's what we're doing when we put it through a lens. It's not quite the same as amplifying sound waves. Now, you can see that light there, and I hope you can clearly see that there's more intensity in the centre of that beam than there is around the outside of the beam. Well, this is exactly what a laser beam is like. It's very intense at the centre and not very bright around the outside. We've shown you this before. It's a piece of wood that's been cut with a parallel slot 26 millimeters deep. This one hasn't quite made it through to the other side because I didn't allow quite enough time. That has been cut with a 2.5-inch lens. But the way lenses work, that just doesn't make any sense at all. Let's go back to the office and we'll talk about that for a minute, and then we'll come back and look at these lenses. Now you can see my dilemma just here. Here's a lens, here's light passing through the lens, and it goes right down to a focus just here. Now once it passes this focal point, look what happens to the rays. They start spreading out. This is the point where, remember, we've concentrated all the energy, we squashed all the light to make it as intense as possible. It is light intensity that causes the molecules to vibrate at a much faster rate. The more intense you can make the light, the faster you can heat or vibrate a molecule. So consequently, once we are past this very, very high intensity point here, the ability to shake the molecules and heat them up gets less and less and less. So how could I produce a parallel slot from a set of rays and intensity that is getting less and less and less? Do you see what I mean? That just doesn't make sense. I've got these lovely new lenses from Cloud Ray. I thought the first thing that I would do, I'll check what happens when a ray of light passes through a lens. We all know that if you dip a stick into water, it looks as though it bends. I mean, logically we know that it doesn't bend and it's an optical illusion of some sort. Well, that optical illusion is something called refraction. A Dutchman called Snell came up with this law called Snell's law. in 1621. That's 400 years ago. Did they have lasers 400 years ago? No. And in fact, he was only the person that has actually formalised the law. Because way back in Egyptian times, ancient Egyptian times, they already discovered this and had got some sort of crude law for dealing with it. And basically what it means, what it shows is that when a light ray passes out of one medium into another medium, it changes its speed and direction. And it is this change of direction, the bending stick effect, that allows lenses to work. So here we've got a parallel ray that's coming into the lens here, and the radius of the lens, because this is a spherical radius, sits at 90 degrees to the surface. It's what they call a normal. So it's come in here parallel through the lens material. Because the ray has come in normal to the surface of the lens, there has been zero effect on its path. So it passes right through the lens cleanly until it hits the second face, whereupon it comes across a face that's at that angle. And when it hits that face at that angle, it veers off to a different angle. And as it bends, it focuses down to coincide with the axis of the lens to meet up at here, something called a focal point. So what I'm doing, I'm actually plotting the focal point of all these rays as I move out from the centre of the lens. And that's what this spreadsheet is all about. Here's the axis of the lens, and as I move further away from the axis of the lens, the focal point gets shorter and shorter and shorter. It does look as though there's something strange going on with that lens. In other words, its focal distance is not remaining constant. Well, until you start looking at these numbers here. It's 99.8 here, and it's 99.85 there. That's about the thickness of a hair. In other words, all the rays from a spherical surface converge on a focal point. There is something called spherical aberration which occurs with lenses. And if we look at this bottom diagram here, here's what happens in reality, which isn't displayed by Snell's law. And that is that we get this strange effect whereby the rays that are coming from the outside part of the lens focus at a shorter distance than the rays that are coming through the centre of the lens, which are here. Okay, so this drawing is rather exaggerated, but it demonstrates the point that the outer rays focus before the inner rays. So you get this interesting effect here. Now, if every ray was exactly the same intensity, you would never get a focal point as such. You would have a bit of a fuzzy focus just about there. With a laser, we've got intensity in the centre of the beam, which is not at the outside of the beam. And intensity is the thing that does damage. The more the intensity, the faster the damage. That's where we're basically starting off today's session in the workshop, trying to investigate what the hell is going on just here. Okay, well, I've just very carefully probed the depth of that lens in there, and it comes out to 94.5. The lens itself was 101.6 supposedly nominal focal point. So 94.6 to 101.6, 7 millimeters is the gap I've got to set below here to hopefully get the nominal focus. Remember I said the nominal gap should be 7 millimeters. I've set this gap to 4 millimeters because I basically want to check that I pass up through the focal point. That's an 8 millimeter range and there's hardly any change. Let me look at that carefully under an eyeglass. And I would say that 4 and 5 are probably just marginally narrower. So that's 4, 5, 6, 7, maybe 8 millimeters is the narrowest one. Okay, so here's that strange test that I was telling you about. After every burst, it's going to step down by 1 millimetre. And that causes a really strange and interesting set of readings. So we're going to run the same test with no lens in at all. This is just the raw beam. Even though the table was dropping down, it's a raw beam, which is parallel. So every one of those marks will be exactly the same. I absolutely love acrylic because it tells me exactly how much hurt it's receiving. Look, in the centre here, we've got the maximum power of the beam, and it's completely clear because we are busy evaporating the material from the centre. Whereas around the outside, you notice all these bubbles. That's where the acrylic has changed to its liquid phase at 160 degrees C. But once it gets above 200 degrees C, which is in the centre here, it's evaporating. Now, it hasn't evaporated very much. If we take a look on the edge of it, because that 70 watts is spread over a large area and the intensity of the light right at the centre of the beam is relatively low and not much different to the light at the edge of the beam. So we're producing this very shallow burn. Now, as I said, I love acrylic because it speaks to me. Sometimes I don't understand acrylic language. I see it, but I don't understand it. In this instance, it's pretty obvious. What does it mean in that instance? So I've had to go away and do some serious thinking about my theory that this here is caused by a focal point way below the natural focal point. I think the work that we've done over the past few sessions, there's nothing wrong with the experiments and the work that we've done. Facts are facts. It's just that I think I have joined the dots up incorrectly and I've come to the wrong conclusion, maybe. But what I've done, I've had to sit down and spend a little bit of time going back, refreshing myself on some of the things that I've just been speaking to you about. The most important thing is the rate at which damage occurs is directly related to the intensity of the light. Now, I'll very quickly run through some of the stuff that we've covered before on previous sessions. Here I've got a Gaussian distribution light intensity curve. Now, the shape itself represents the light intensity from 0 to whatever 100% happens to be. In this case, I'm going to assume that that power, which is the area under the curve, represents my 70 watt tube that I've got here. Now, if I was to go out and buy a 140 watt tube, I would have twice as much power, which means I've got to have twice as much area under this curve. The curve will still satisfy the requirements of the Gaussian distribution formula, and in doing so, doubling the power will also double the intensity. But it's changed something else as well, you'll notice. Not only has it doubled the intensity, it's doubled the relationship between the maximum intensity and the rest of the shape of the curve. This is now a more pointed curve as opposed to this blunt one. So let's just take a look at my 70 watt beam. And here it is. It's a Gaussian distribution, which looks like this. It's very, very sharp. Okay? Now, if I reduce the power in the beam to 90, 80, 70, 60, all the way down to 10%, then this is no longer a sharp beam at 10% power. In other words, as I reduce the power in the beam, it changes its shape, its relationship between 0 and maximum intensity. So this area here represents 7 watts, 14 watts, 21 watts, all the way up to 70 watts. The area under this graph here is 70 watts. if I get a non-Gaussian curve, like this one here, then if I do the same thing and take it up to 70 watts, look, I've got basically crap intensity. I haven't got a sharp, high intensity graph. I've got a blunt intensity graph, very similar to, well, it's even worse than what I'm getting here at 10% probably. It wouldn't even perform as well as a 10% Gaussian curve. The power is relatively unimportant. The most important part is how your tube is tuned by the manufacturer. Is it tuned to give a nice Gaussian distribution, or is it somehow badly tuned and giving something like this? I've divided this Gaussian distribution into 6, and if it was a 6mm beam, then this central 2mm contains 70% of the power that's under that curve. But what I've just told you was that power isn't necessarily the same as intensity, only when you've got a good Gaussian distribution. So we're going to take this 7mm beam and we're going to put it through a lens, and we're going to squash this 7mm down by a factor of 100. We're going to amplify it by a factor of 100. And just at this point here, we shall still have this Gaussian distribution. Here's our Gaussian distribution. Here's a 4-inch lens. And if I have got a 4-inch lens, then the spot size, i.e. the point at which I can amplify it down to, is roughly, say, 0.3mm diameter. For a 2.5, 2 and 1.5, those spot sizes become smaller. Now, these are the theoretical spot sizes, not real spot sizes. So what I've done in this graph here is to take that Gaussian distribution, and I've reduced the base from 7mm down to 0.3. To get 70 watts worth of area, where I've only got a base of 0.3, means here's what I've done to the graph. Let me just show you that in real scale. The 4-inch has now extended its intensity to some stupid value right out here. The 2.5 has done that. 2 and 1.5 has now come way, way out here. Now, I want you to bear this picture in mind, because I still think we've got a little bit of a conundrum coming up. But I'm having to rethink this problem, and I'm going over this old ground because, as I said, I think I have joined the dots wrongly at the next stage. At some point a little while ago, you may remember me producing this. I fired the raw beam at a block of acrylic for 10 seconds. I produced a burn that was virtually through the block, 25mm. I then put a 7.5-inch lens into the beam, but I didn't focus the beam down onto the block. The focal point was down here. And what I did, I put the block halfway down the beam, roughly. And so consequently, I had a mode burn that was like this. Now, this pointed bit here is not a focal point, but this pointy bit in here, which is shown here, is not a focal point. We can see that clearly. Did I take any notice of that? No. I've blindly gone on and followed my imagination, that because I see a hole that looks like that, that can only be caused by a beam being focused like that. In other words, this deep hole here can only be caused because there is a beam of light that's below the focal point which is still wanting to focus. Now, this little block of acrylic has been sitting on my desk for the last 3 months, and I haven't really been listening to it. It's been laughing at me, but I've not been listening. I've been blindly going on with the idea that this pointy bit that I'm seeing below the focal point is caused by a second focus. We can see here that I've achieved this, and here, pointy bits without a focus. This one's got no focus on it at all, and this one, the focal point is way out here. What we're actually seeing here is the distribution of light intensity within the beam. The greater the light intensity, the faster you can do damage. Every one of these is 300 milliseconds worth of damage. What I'm really looking at is a series of mode burns, each of which is taking place at a different start point below the focal point. This piece of acrylic is clearly telling me what's happening, how much it's hurting, how much damage is being done, what the intensity of the light is, every point in that picture. So we've got to go and analyse that to try and work out if we can reverse engineer the damage and fit it into this picture here. So what's really going on with my tests here? Well, what I've done, I've gone away and I've drawn accurately the first 4 of those spikes. If I expose a 1.1 millimeter diameter spot size just here at the nominal focal point, I mean, we just really don't know where the focal point is. It could be anything from there to here. This is where it may be, but that might not be where I've actually set the focal point. It could well be that I set the focal point just here as 0, and what I've actually got here is a 1 millimeter spot size. We've put 70 watts into this incredibly small footprint, and therefore the intensity has shot up way over to the other side of the workshop there. Some phenomenal value. It's such a high intensity that in 300 milliseconds, that central spike of intensity is able to burn its way 22 millimeters deep into this material. Well, we have the luxury of being able to step through the video in 20 millisecond intervals so that we can actually watch these spikes growing. There's the first 20 milliseconds of growth for the very first spike. And 2 things you might be able to notice. First of all, it's got quite a large footprint across the top here, but you can see the spike is, first of all, very pointed just here, but it's growing quite quickly, because it's not until you see 2 of these growing that you begin to realise that there's a sort of pattern developing. Okay, now you can clearly see what I'm talking about, this incredibly high intensity spike of power. Now that can only be caused by light at the centre of this mode burn, but look, you can see how the footprint at the top here has already grown quite large. It hasn't shrunk, it hasn't come down here yet, but it's already large on the surface. So as we get more time, more exposure, what's going to happen is this lower power, which is out here, is going to start burning its way onto the picture. And we should see that happening. You'll see this starts to slow down as it gets deeper, but this starts to grow more. So you can see how this is beginning to widen up now. Look, can you see the cone beginning to appear here? And now look, we've got our definite cone shape. And you can see all these fumes inside the tube here. But look, we've still got a very, very, very sharp point just here, which means we must have a central beam of light which is passing right through the centre there to burn and damage that far down. It's very, very intense, which is why it's doing more damage here than it is up here. There's a second burn. Again, look, you can just about see the difference here between the size of that footprint there and this one. Now, that hasn't fully developed as a footprint yet, I don't think, because that is just the first hit. And already that looks wider than the first one that we had. So let's just follow this through. And again, if you watch, don't watch this bit down here, watch this bit up here and watch the way it grows. See how it's coming down here quite substantially now to a much shallower funnel. Now, it's really strange that this next one looks as though it's already slightly fatter than either of these two at the start. But again, it's got a smaller footprint here than either of these two. So let's just watch the way in which this develops across the top here. Look, we've definitely got a very, very thin stream of very high intense energy right down the centre of the beam, which is why it's piercing so sharply and so deeply. But it's what's happening behind that's interesting as it moves away from the axis of the beam. There's a little less power there, but there's still a lot of power there to start opening up the hole if you give it enough time for that power to do some damage. So this is all about exposure time. Okay. Again, now look, this is very fat here, right at the start, and a sharp point. What does very fat mean? We've got less difference between the energy here and the energy here. We've got very high energy here, and we've got slightly higher energy here, because we're doing a great deal of damage in that area. You'll find that this very high power here is following this incredibly high power right at the front. We haven't got the long thin spike that we had with these. We've got much more of an icicle shape, and we should probably find that icicle shape following right through. Let's just check. Yeah, and now look, you'll see that what it's doing, it's actually got this icicle shape here, but it's leaving a parallel hole behind it. Now we do the next one. And again, look, we've got this same property. We've got a very wide beam, relatively speaking, to start with. There's not a huge difference between the energy at the outside of this burn and the energy at the centre of the burn, because otherwise the centre of the burn would already be down here. We'll expect that that shape will follow as the beam grows. Okay, I think I already see a pattern there. We'll go one more. It's very difficult to decide which of these is the best one. When I look at the damage at the top, I would say that that one is the smallest entry. If you remember, I set the focus at 8mm, but I set that at 20mm a second travel speed. Here we've got a travel speed of 0. So that probably accounts for why we've got this tapered inlet here, meaning that I have not set the focus correctly for 0 speed. For 0 speed, I need to set it maybe here, 2mm lower at 10mm. This is a 4-inch lens. It possibly should have, theoretically, a 0.3 spot size. Well, if I look at this spot size here, in other words, the smallest point at which all rays are passing through, that looks to be, I think, around about 0.8, which is 2.5 to 3 times more than the theoretical. So that means the intensity is not going to be quite as great as my diagram indicated. But as you can see, it is pretty intense because it's able to pierce very quickly a very thin line right through the centre of this tube. Now, I should be using exactly the same power, exactly the same test, exactly the same time. The only difference between this 4-inch lens and a 1.5-inch lens that I'm going to test next will be the spot size of the entry point. Now if the spot size is a quarter of this, what it should mean is that I've got an even greater intensity of energy right at the centre of that spike, and for 300 milliseconds this should drop right through to the table. I somehow think that isn't going to happen from previous experience, but we're going to give it a try. Okay, so I've got a 38.1 lens set up in here now, and we're just going to check and find out where the focus is. Now I've measured how far the lens is inside the nozzle, and it's 10 millimeters. We've got a 38.1 lens, so that means there's 28 millimeters outside the nozzle down to the work. Now I'm going to set this minus 4 millimeters to 24 millimeters to try and find the best focus in the middle of my pattern. So that's 24, 25, 26, 27, 28 is the thinnest line. So that's exactly what we expected. So while you've still got those last step through pictures fresh in your mind for the 4-inch lens, let's take a step through for this 1.5-inch lens. Now remember, we're expecting to see the beam go and straight out the bottom of here. So here's our first step. Oops. Now compare that to the first step we saw with the 4-inch one, which was a spike right down here. So we've already got a very blunt mode burn beginning there. Look at the diameter of that. Now we're beginning to develop a bit of a spike. And it looks a bit like the mode burns that we saw for a raw beam. Yeah. We're developing some length and we're getting a very sharp point here. So it could well be that what we're seeing here is a typical Gaussian shaped beam, because this is the correct form that we'd expect to see for a Gaussian mode burn. Hang on, that's it. Well, that didn't get very far, did it? So look at this footprint on the top here. We're expecting to see the footprint of the Gaussian distribution to be a spot size which is a quarter of what it was for a 4-inch lens. This is the same or maybe even bigger. And here we are, we're starting off exactly the same way. A very short, stubby entry. It's beginning to get sharper quicker. And now we're developing that central core. Is this the one that's going to go right down the bottom? This is a very, very long conical shape, but it's slightly narrower conical shape than this one. But now you'll see something else that's beginning to happen down here. Can you see the way in which this is beginning to balloon out a bit rather than this one, which was more or less parallel? And that's it. Didn't quite make it as far as our first 4-inch spike. Now here's our first hit here. Now it looks to be a little bit longer and a little bit sharper. These look to be much larger than the footprint that we've got here. But hey, we haven't seen it develop yet. It's developing quite quickly and it's got quite a leading sharp point. Whoa, hang on, what's going on here? It's that ballooning effect again. it's actually made it deeper. You see, this is interesting. Number 4, first of all, we've got a much smaller hole. And secondly, the first pulse, look what it's done. It's squirted right down to here with a very, very high intensity beam. Squirted right through there in one pulse. But something else that's already beginning to happen on the second part of it. Look, we've already started to get some ballooning here. Look, we had this ballooning here. We had even more ballooning on this one. And now we've started to get ballooning right up here as soon as we start. What's causing this ballooning? Well, look, the rays that are coming in at this angle here are coming in cleanly, and then they're coming down through this thin section here. We're evaporating this inside surface away with the rays that are coming through this fairly thin neck just here. For this amount of ballooning to happen right down here, it means that not only have we caught these rays here, we've also caught some rays that are coming down just off centre as well. So this is doing what you might expect from a diverging beam below the focal point, but that's a diverging beam that is just off centre. Here we've got a very deep funnel. Now the funnel is getting shallower and shallower and shallower. So does that mean to say I'm set a long way below the correct focal point? Because look at the footprint on the top here. It's getting smaller as we move along. Does that mean to say I'm at least 1, 2, 3, maybe 4 millimeters out of focus? Which is quite incredible for a short focus lens. This one here is very interesting, because look how sharply that spike has come in. It's almost implying now that we've reached, or on the process of reaching, a focal point, because we have not got much of a footprint here, and we've got a very sharp point, which indicates that we've got high intensity of light down the centre and not much at the edge. So we've got a much sharper beam this time, whereas here we had a much blunter beam. Now hang about. We can already see some ballooning taking place here. And that's it. Not very deep at all. So although you can see here that this is a much smaller footprint than any of these, that entry point there is probably still, I don't know, 0.5, maybe even more than 0.5. And it would indicate, as we're seeing here, that we're still out of focus. Because realistically, if the focus was absolutely correct, we should have this very small diameter on the surface. Now, we've just caught the end of a frame, but a very, very sharp entry there. Let's just have a look one more frame on. Let's move on a frame. Yeah, it's smaller, but look what's happening here. We've immediately got ballooning, immediately. So this clearly indicates that we've now probably reached the focal point. It does look as though we've got a very, very small entry point here. And now what we've got is ballooning after the entry point, because we're getting these sideways rays which are eroding the sides of the tube. And as you can see here, look, we've come right up to the top here now with our ballooning. So I suspect that the next one will be worse. In other words, it'll start to get bigger now rather than smaller. In other words, my focal point is actually 1, 2, 3, 4, 5 millimeters wrong, even though I set it at 38.1. A bit of a blunt spike developing here. So that would indicate that we're starting to get a much bigger footprint, entry point, spot size, call it what you want. Yes, when you compare this with what we're seeing here and here and even here, we're past the focal point now. We're below the focal point. We'll just watch another one and it should be even thicker. Oh, that's it. Terrible, isn't it? Look. Now, let's just come back and look at this one here, which is not very pretty. So I'll just remind you again that here's what a 4-inch lens looks like when I convert my 70 watt intensity diagram to 100%. Here's the intensity that I'm going to get relative to 0. When I take a theoretical 0.07 beam spot size, and again 70 watts, convert it into an intensity diagram, that intensity diagram finishes up over there. Now that appears to be total rubbish because we've just seen those numbers, that theory just does not stack up. We're not getting huge intensity just because we've put the beam through a very short focus lens. Although this 1.5-inch lens has got a smaller footprint than our 4-inch lens, it still didn't develop a larger intensity than the 4-inch lens. Why? What's wrong with this theory? Now look, you can clearly see from that image there that 38 millimeters is the perfect focus for that lens. Okay, so I'm running this at 20 millimeters a second, which is a pretty reasonable cutting speed. As I commented when we went through the step-by-step. 1, 2, 3, 4, 5 millimeters, I'm out of focus. You've just seen me prove that this lens is focusing perfectly at 38 millimeters. So I'm now beginning to doubt that what I'm seeing is out of focus. What I'm seeing is the result of a secondary focus which is gradually coming to the surface here that we're seeing. 41, 42, 43 millimeters, that we get what appears to be the correct focal point. And then after that focal point, all of a sudden, things start to turn brown and runny. So I think that actually I haven't joined the dots up incorrectly. So I think that what we're seeing here is a combination of a mode burn, which just gives us these long spikes, but secondary, we're seeing this focus, which possibly might be a focus, a secondary focus below the focal point. Now, I started off this session anticipating that my theory of lenses might be taking a nosedive. Perhaps there isn't a secondary focal point beyond the natural focal point of the lens. This seems to be showing me something different. So I've got a little bit of a smile back on my face. Next session, we're going to have to prove by repeating the same test for a 2-inch and a 2.5-inch lens that we can actually find that this focal point is actually moving further along here, i.e. we're getting a longer focal point below the natural focal point, which is what this diagram seems to be showing us. Now we've still got a huge amount to learn about how lenses actually cut materials. They were never designed for cutting materials. They were designed for focusing light, uniform light, onto a surface. For instance, for telescopes, for normal photography, and for certain scientific work. We're using them in a completely different way. If a lens only does what it was designed to do, it would focus the light onto a surface and we would be able to scratch it and engrave it. The fact that we can do things like this with it tells us that there's something else going on when we start using a lens to amplify intensity of light, not just light. Because what we're seeing here is an amplification of intensity of light. The intensity of the light is doing more and more damage to the material. So at that point I'm going to say goodbye and thank you very much again for your time and patience.